It's me, Professor Aaron Albert, here again with lesson 22. Let's learn some econ. So today's goal is to show you how to fully solve a 2x2 exchange economy, i.e. an Edgeworth box. You'll remember that the problem is defined as thus. Jane has 20 candy and 30 wood at the moment that she wakes up on a desert island, and Denise wakes up holding 20 wood and 60 candy. They have preferences represented by indifference curves like this, and they try to figure out how to optimally ration their candy and wood between the two of them such that they are as happy as possible. That was how we found the contract curve, right? We tried to find points such that one girl could not be made better off without harming the other. Now we're trying to figure out what would happen if we let them trade competitively. We let them set up a market and trade until they no longer wanted to trade. You'll remember that the contract curve gives us the set of Pareto points through the middle. Tell me, what graphical property finds us these contract curve points, and mathematically, how do we go about finding those points? Answer it. Hopefully you remember that these contract curve points were found where their indifference curves were tangent, and we can find that by doing a Lagrange optimization whereby we maximize, for instance, Jane's utility subject to Denise's utility hitting a certain level. If you do this, you will find that it can be solved by setting Jane's MRS equal to Denise's MRS, which matches our graphical intuition, namely the indifference curves have to be tangent. You will note that one of the appealing points was F. Think for a minute how Jane and Denise could trade such that they went from points E to F. What actual goods change hand, and what does this suggest regarding the value of those goods? You'll note that between points E and F, Jane gives Denise 20 candies. Denise gives Jane 20 candies, and Jane gives Denise 10 wood. Therefore, Jane has traded 20 candy for 10 wood, so it seems to me like candy is worth twice as much as wood. That is, if you let them set up a free market, and we believe that they arrive at F, that suggests their equilibrium will be given by wood having a price of 2 candy, or candy being worth half as much as wood. So, something interesting happens if we draw a line that reflects this price, this 2-to-1 ratio. If you draw a line between E and this point F, you'll note that this line reflecting the price between those 2 points is tangent to both indifference curves on the contract curve at point F. So this is our competitive equilibrium. You'll note that if they trade from point E to F, there is no additional gains from trade possible, right? There is no further lens from their indifference curve overlapping, and therefore they will stick at F and be content. So with this in mind, we're going to set about showing you how to find the competitive equilibrium. To do this, there's going to be 2 big steps. First, find the contract curve. To do that, apply the skills we learned last time, namely maximize one person's util subject to the other person's util hitting a certain requisite level of happiness. And if you simplify that, you'll find that this just means setting MRS1 equal to MRS2. Then find the actual allocations that will result from trade. To do this, you're going to need to solve each person's quantity functions. That is, find out how much Jane and Denise desire of good 1s and good 2 as functions of their price. You're going to let the price of one good be 1, i.e. let that good be currency, and let the other good be valued at just price. The budgets will then look something like this. However much money you have is going to be equal to how much good 1 you have times its price, which is 1, times how much good 2 you have times price, which is either P or P2. Once you've set up the problem like this, all you have to do is apply the Lagrange optimization tools you had from block 1. Then, after you have demand, i.e. good 1 and good 2 desired, as functions of price for both players, you can then use the quantity 1 and 2 total for both players to find the optimal price by looking at the total amount of good 1 and good 2 that are found in the economy in total. This sounds like a lot of steps, so let's do it for real. So first, note that we are given util functions, namely that UA is given by QA1 to the 0.8, QA2 to the 0.2, and QB is given by root B1, B2. What type of indifference curves are these? Hopefully you note that these are, obviously, Cobbs-Douglas utils. Also, let player 1 be endowed with 6, 5, and let the total on the island be given as 20, 10. With these endowments, what is the total and individual endowments for both players? Hopefully you note that we have 6 good 1 at the first person and 20 total means player 2 must have 14. Similarly, player 2 must have 5 of good 2. So now we have the total amount of quantities for each player. The first thing we should do is solve for the contract curve. How do we do that? Hopefully you'll remember that in order to do that, we must set MRS1 equal to MRS2. To find the MRS in this case, it should be relatively simple because we've played with Cobbs-Douglas dozens of times. Namely, just find the first derivative of UA with respect to good 1 and divide that by the derivative with respect to good 2. If you do that, you'll find that the MRS looks like this. Then perform similar for the second player, and you'll find that it looks like this. Can these be simplified? Sure. If you go ahead and plug the quantities total on the island, namely player 2 has 20 minus how much player 1 has, player 2 has 10 minus how much player 1 has, you could then do some algebra to greatly simplify this equation. I will leave looking over the steps for this algebra to you guys, but if you do it, you can find that good 2 for player A should be equal to good 1 for player A divided by 8 minus 0.3 good 1 player A. Next, although this gives us all points that could happen at equilibrium, i.e. that traces out our entire contract curve, we should take a moment to figure out exactly which point would hold in equilibrium. In order to do that, all we have to do is apply the consumer demand optimal quantity 1 and quantity 2 like we did in block 1. So the first thing we need to do is figure out what the budget is for player 1 and player 2. To simplify, remember that we're going to let P1 be given as 1 and P2 be given as P. That is, good 1 will be viewed as their currency. So how much total value does player 1 have to spend? And then answer for me, how much total value does player 2 have to spend? Hopefully you note that player 1 has 6 of good 1 plus 5 of good 2. The value of that must be 6 times the value of good 1, which is 1, plus 5 times the value of good 1, which is 5 times P. Therefore, no matter what player 1 buys, it better total 6 plus 5P. Similarly, player 2 better not exchange for any more goods than is valued by 5 plus 14P. And what must be equal to these total values? Well, the total value of the stuff they demand. That is, player 1 will demand QA1 and QA2, and player 2 will be looking to purchase QB1 and QB2. And you'll note that on both the left and the right-hand side of this equation, we are remaining standard that good 1 is valued at $1 each, and good 2 is valued at P each. So therefore, the total amount that player 1 demands, QA1 plus PQA2, must equal the total value that they've started on the island with. That is 6 plus 5P. And similar for player 2. Once we have these budgets, how can we go about solving for the optimal quantity demanded for players 1 and 2? Just apply the skills we learned in block 1. I am going to cheat by using the Cobbs-Douglas formula from our textbook. Namely, given some budget and some utility functions you can just plug in and you'll get values like this. If you want to practice finding optimal quantities demanded with Cobbs-Douglas, go ahead and do it. Hopefully you come up with these answers. So after you've done that, lots of Lagrange work and lots of algebra, you will find that QA1 and QA2 are given as thus, and QB1 and QB2 are given as thus. So this is great. We've found the quantities demanded by both players as functions of price. However, those don't give us numbers. Is there any way we could relate the quantities of good 1 demanded by both players in order to find the actual numbers that they demand? Similarly, is there some sort of equation we could use that would unite the quantities demanded for good 2 for player 1, A and B, in order to find real numbers? Well, here we can lean on the fact that the island has a fixed quantity of goods. We know that the island only has so many units of good 1 and good 2. So we know that the total value of good 1, i.e. 0.86 plus 5p plus good 2 for good 1 for the other player, half of 14 plus p5, that must in total equal 20. Why? Because they only have 20 units of good 1. If you do this, you'll find that p equals 1.26. And if you plug p equals 1.26 into these equations, you will find the total number of goods that is demanded by both players. Although here I have found the price looking at good 1, you'll get exactly the same answer, namely p equals 1.26, if you evaluate the same way looking at good 2 for both players. If you then plug 1.26 in, you'll find the total value of goods demanded by both players. And hopefully those two values will sum to the amount on the island, and that solves the problem for us. So to recap, anytime you have a full Edgeworth box problem and you want to solve for the full equilibrium, 1, find the contract curve. That's going to be where MRS equals MRS for both players. 2, find the price line. In order to do that, you're going to solve for the demand of both players for both goods as functions of price, and then use the total amount of the good on the island to solve for the actual price. And then if you plug that price in to their demand functions as functions of price, you'll find numbers for both players. The full equilibrium then is both the Pareto optimal line, i.e. the contract curve, as well as what they would trade for in equilibrium, i.e. the competitive quantities found in step 2. The rest of today's lesson will be you guys trying some additional exercises. Please work through this problem and let me know how you do. Good luck. Bye.